Yeah.
Should I turn the light off, or what do you prefer?
Yeah.
Sorry?
Yeah.
Yeah. Oh, it's dimmable. If you, I think. Yeah.
Yeah, that's good.
Oh.
Yeah.
Okay, so I actually realized after last time that I would probably need more examples to follow the formalism that I'm using. So I squeezed in more examples, and hopefully it will be easier to follow. So remember where we left off? We reviewed the linear bifurcation analysis, and now we're trying to really find how a branch which is sitting close to a normal branch. We're trying to find this bifurcated branch by expansion. And so you might have forgotten things since last time, so I think I'll review very quickly the IDE. So the first thing we need is these operators. And again, I'll give you specific examples where all this really makes sense. It's the ith variation of the energy, which you obtain by repeatedly linearizing. And it's evaluated on the branch level, on the fundamental branch. And because it's the ith variation, it takes I increments in input. And maybe I should also explain again this notation. So let's take the second variation, for instance. And again, you'll see on examples, the second variation is something that depends on, so here implicitly, on the load and where you are, and it also takes two increments. So actually this can typically be represented as a matrix in the discrete case, and my dot square bracket notation means that, so the matrix is the case where you have two variations, so that would be A dot x1 dot x2. Okay, so that's anything which is multilinear with respect to the argument. Now, there are only two sides to a tensor, so that's hard to generalize to higher dimensions. So some people use this notation, and then you add more parentheses as you add more arguments. So well, this notation maybe has the advantage of being more explicit, but it becomes clumsy when you have 4 layers of parentheses. So I tend to prefer this one. Okay, it's a little bit more abstract. Okay, so we have these variations of the energy, which again are evaluated on the fundamental branch. that was an example with, using the Rayleigh-Taylor instability. You remember it's the elastic slab, which is hanging below a rigid plane. So we don't need these for the moment. And that I will come back to this later when I need it. So I think, yeah, so now probably it's a good time to look at this for the elastic gas. So remember the elastic gas given by this energy. So W would be the constitutive that you use for bending. So you can think of W being a quadratic function if you're using linear elasticity, but that's not required. Then the fundamental branch would simply be theta not equal 0. And then you can calculate the variation. So for the variation, each time you substitute theta by some small increment, and you linearize with respect to the theta 1 or h. That's the same. So the first variation would be this with an implicit argument. Then I'm dropping the argument theta prime for W prime, but it should be there. You get this. Does anyone want me to derive that more slowly, or it's fine? Okay. Then the second variation. So now the first increment is called theta hat, and the second variation introduces a second increment, which is theta 1, and you get that. So it's a quadratic function. And to get the Q forms, you have to evaluate on the fundamental branch. So it means any theta which is neither hat nor theta 1, you take it to 0. So for the first branch, you find that this becomes 0, and then the W prime, which depends on theta prime, is also 0 because theta prime 0 is 0. So this is 0, and you get 0. That's actually because of symmetry. And you do the same for all the variations. So for this, we evaluate the coefficients here that depend on the base solution in the base solution. So this one would be the initial bending modulus, W second, and this would be 1. And that's how you get Q2. Next, we'd also need Q2 prime, which is the derivative with respect to lambda of this. So it takes all this term. And we'll actually only need it when the two arguments are equal. So that's why I've used this notation. And then same for Q3, which you get from the third variation, because everything is symmetric with respect to top, due to the top-down symmetry. You find that the coefficients here and here are 0. And here we are assuming that the bending energy W is an even function of theta prime. So that would be 0 for Q3. And Q4, one more variation, and you have that's a non-linear elasticity modulus. Okay, and we see that it's important in this non-linear theory. And then you have another coefficient with minus 0. You evaluate that on the base, on the fundamental branch, and you get this. Okay. So this is just a matter of calculating the successive variations of the energy, evaluating them in the fundamental branch, and sometimes, whenever needed, taking the derivative with respect to lambda. Okay, and the final thing before we use them is that we'll actually need them at the bifurcation point because we're doing an expansion at this bifurcation point. So ultimately, we'll also replace lambda by its critical value. Okay, so now remember the expansion uses eta as a bifurcation parameter. So we have that fundamental branch. We are lifting off from a critical point, and then we are using the arc length eta along this bifurcated branch. And so, and now we are just inserting these two expressions into the nonlinear equilibrium that uses this x hat as a virtual displacement, and you can even do that in the computer. It's just a matter of expanding and finding the various terms. So that's what we get. And now the idea is to solve for the xi's and the lambda i's, which are the unknown coefficients in our expansions, order by order. And you see that the problem has a nice structure and can be solved using a recipe. So let's look at the order eta first. And we said that this Q2C, and actually we can look at it for the elastica. So the Q2C would be this, with lambda equals 1, and then you recognize the linearized equation of equilibrium, which we have solved to determine the critical load. Okay, so the point is that you requesting that this Q2C is equal 0 for any theta hat is the same thing as we did already when we solved the linear bifurcation problem. So that just tells us that x1 is the same x1 as the critical node from the linear bifurcation analysis. Then to order eta squared, we have a problem. So now x1 is known, and the unknowns are lambda 1 and x2. But we have to recognize that it's not possible to solve this problem because this QC here, you can think of it as a matrix. By construction, this QC is singular because we know that it has this x1 living in the kernel. So we can't solve this type of singular problem without first verifying what's called the solvability condition. So a necessary condition for this problem to be true is if you replace x hat by x1, in particular this should be true, and the benefit of doing that is that because of this equation that removes this term. Okay, so we get a necessary condition for that to be solvable. And if you do this, so you insert x1, well, you set x hat to be x1 here, you get rid of this term, and you have one equation that now only has x1. So this is known, x1 is known, this is known also, and so you get an equation for lambda 1. Okay? And usually you stop here because lambda 1 is the most interesting thing. Well, it's the first thing that you want to learn. It's actually the slope, and we see that on examples. It's the slope of the bifurcated curve. So now if you know this, that's a parameter, that's an arc length parameter, you know this, and you know this, so you know the two terms that start your expansion of the branch, and you have the beginning of the branch. But you could go, you could continue. Now there are many problems for which this operator is actually 0, and we've seen that it's the case for the elastica. And actually it's basically any problem where there are underlying symmetries, this is going to be 0. So what that gives you is lambda 1 equals 0. And so if you have lambda 1 equals 0, you don't, at this stage, you can't connect the parameter eta, which is a virtual parameter, to an increment of load. Okay, so that's not very good because then you still have the start of the expansion here because you know x1, but you don't know what eta is and how it's connected to the load, to the real load. So you need to go further. And so that's what we call the symmetric case, where by definition the symmetric case is when this thing evaluates to 0, and again that's a case which arises often in practice. Then we need to look at the next order. Well, actually, before we need to look at the next order, now we are in a position where the solvability condition for this thing has been verified. So we make sure that the right-hand side here is in the image of this operator. And we can go ahead and solve for x2. So we have to solve this new problem, which is like the previous one. And so that it's written in a weak form, you have to integrate by parts, and typically you'll find the second order correction to the displacement x2. So that's something which is easily forgotten. And actually, if you don't do that, it can lead to wrong results. For symmetric bifurcations, you absolutely need to find the subdominant correction x2 to the displacement before you can even calculate the amplitude of it. Okay. For non-symmetric bifurcation, it's different, and we saw that we have a formula for lambda 1 that only depends on x1. So that's why symmetric bifurcations are a little bit more complicated because of this extra step where you need to calculate x2. And then you do the same trick as before. You continue actually the expansion. You look at these third order terms, and again it's the same singular operator that that determines x3. So again, this equation is not solvable in general because this is singular. So we need to check that all this lives in the image of this guy, and we do this by the same trick, replacing x hat by x1. And so we have to solve all this equals 0 with x hats replaced by x1. And now that's quite easy, actually. We have this term which we keep, this term which we keep, this one which we know and will give us an equation for lambda 2. And these terms are all proportional to lambda 1, which in the symmetric case is 0. So that's 0. And this is 0. So we are left with that equation, which has lambda 1, and anything in the brackets is known now. Okay? And in particular, note that there's this contribution here that comes from the second order displacement, which we've just determined. Okay? So that gives you lambda 2. And now we are in the symmetric case where the expansion actually reads lambda c. There's no term of order 1 because we've shown lambda 1 equals 0. Okay, so if you know lambda 2, then you can connect eta to the change, to the increment of load. And by the way, you see that the sign of lambda 2. So this is the case of the symmetric bifurcation, right? So if lambda 2 is positive, that means that the critical load lambda on the bifurcated branch is larger than lambda c. So that's the case where the curvature of the bifurcated branch is to the right. And conversely, for the symmetric bifurcation with a lambda 2 negative, the bifurcated branch is giving to the left. So usually that means this part of the curve is going to be stable and this one is going to be unstable, but I said I wouldn't comment too much on stability. Okay, so bottom line is that we have a recipe that just involves plugging these expansions, calculating the operators, and then we have these rules that gives us the first terms of the expansion. Okay, so I'll refer to these rules later on. And so technically, it's a little bit more difficult than the linear bifurcation analysis, essentially because we have well, these operators can be a little bit complicated to evaluate, but typically we would rely on simple calculations. And if you do that, you have this. So let me show how this can be applied. So now I look at the elasticand, which is the symmetric case here, and we'll just do. So remember the operators we've just used. It's pretty straightforward, and let's look at the symmetric case. So we've solved the linear bifurcation mode last week. That is readily checked just from the, we have seen that Q3 is 0 for any argument. So we are in a symmetric case. We've seen that this implies lambda 1 equals 0. So the expansion of the load is like this. And we have to solve for x2 here. And that would be the right-hand side. But in our specific case, Q3 is 0 for any sets of increments. So that's actually 0 for this particular problem. So it's a very symmetric problem. And then x2 can be set to 0. And finally, we just need to evaluate that, right? But now x2 is 0, so this term goes away. So lambda 2 is going to just be the ratio of this Q4 and Q2 prime. Okay, so we have Q4 here. You have Q2 prime here. And you just have to plug the form of the linear mode, which for that particular set of boundary conditions is like that. And then the only difficulty, well, it's not really a difficulty, is so theta 1 prime would be an unknown amplitude A times this sign. All these operators have the integrals, so you need to calculate the integrals of sines and cosines and powers, and you just get this. Okay? So the lambda 2 prime is multiplied by a Q2. The Q2 is quadratic with respect to θ1, so it's quadratic with respect to the amplitude. So you get amplitude squared times the coefficients times lambda2. And this is Q4, which is, it takes 4 arguments, so it's the fourth power of A. And at the end of the day, you get this equation, which is typical for symmetric bifurcation. This is lambda2 A squared plus some coefficient times A for 0. So it's usually presented by dividing by A. What we can do here is multiply. This is an equation which we've read at order eta 3. So if we multiply by eta 3, we can write this as and then eta A, we recognize. So that's the mode at which, by assumption, we multiply by eta to reconstruct the true solution, right? So this is the same eta that's here. That's the mode it gets multiplied by eta. So eta A is the true unscaled amplitude, right? So in my notation, this will become A plus some coefficient which we computed equals 0, and this we recognize that's the up to coefficient, that's the increment of load. So I'm not concerned for coefficients for the moment, but that's essentially lambda minus lambda. Okay, and all this calculation allows us to calculate this constant. So you probably recognize here the equation for our system in the load amplitude. That's what gives us the bifurcation equation, right? We have one branch which is A equals 0, that's a solution, and we have another branch which is quadratic. So that's how we can finally plot the bifurcation diagram. Remember that all this was done in perturbation close to the bifurcation point, so that's actually what we calculated here is the oscillating parameter to the true branch, which we could still determine by extensive numerical analysis. Okay? So that was the first example in the symmetric case. And now I'm showing you a second example, which is non-symmetric, but has an additional difficulty that now there are multiple modes of bifurcation. And I've implicitly assumed that there was a single mode. So I need to tweak a little bit what I've shown. Okay, so what I'm talking now is the Rayleigh-Taylor instability. So I'm coming back to it. So this is a hard plane. This is an elastic slab, and it's subjected to its own weight. And in some conditions, we've seen in the experiments that it can become a mistake. So if you remember, we did the linear stability of this. So now I'm looking from below. So this would be Z, X, and now that's X. Okay. We did the linear stability analysis, and we found that there's a free direction but a fixed norm for the unstable wave numbers in the horizontal plane. And associated with that, we have striped modes, right? But we have an infinity of these modes because the angle theta is undetermined. So that's a problem that, because of the underlying symmetry, has an infinity of buckling modes. So the linear bifurcation problem formally writes like that. And okay, so it's an infinite superposition, but we'll see that it's enough to focus on finite superposition of sinusoidal modes. So think of n as being infinite and that in an interval if you want. But the solution of our linear bifurcation problem is this, and it's superposition with amplitudes that need to be determined and will be determined later, but are unspecified for the moment, times these linear modes, and the y1 of theta is the solution I've outlined. Okay, so y1 of theta is the 3D solution that the 3D mode such that the wave vector has this angle, makes this angle theta in the horizontal plane. Okay, so now the question that we can tackle by going to the next order is what would be the preferred directions and what would be the amplitudes and how do they couple together. So the question is really now how will these modes cooperate and why do we observe in the experiments a specific pattern which has to be some specific combinations of these modes. Okay, so let's just do the recipe. So now if we go back at the expression of Q2, which we've seen before, remember the argument that Q2, so when we derive the amplitude equation for the single mode case by replacing x hat by x1, remember? I could go back to this, but it's maybe not necessary. I'll show you. Right, so in the symmetric case, we didn't solve this entire equation. We say that we can replace x1 here, and then that goes away. So we have an equation that connects x1 and lambda 1. So that's no longer possible. Well, we have to explain a little bit better what we are doing here if it's a multiple mode case, because there's not a single x1. There are multiple, many of them. So and again, the goal is to have to remove this term so we can solve the other terms. So actually, you can remove this term if you take x hat, that's any combination of the linear modes. Right? So in this equation, you can introduce hat amplitudes, virtual amplitudes, and insert into that equation. And now if you look at the other terms, the two other terms which are here, this is what you get. Okay? So now this equation is linear with respect to the real amplitude, linear with respect to the virtual amplitudes, quadratic with respect to the real amplitudes, and linear with respect to the virtual amplitudes. And you can actually view it as, so if you now think of these a hat as increments, you can think of this as the gradient, if you want, the first variation of the functional, which is this one, and it's easy to check. Okay, so that's essentially this is a hat times, well, formally this term looks like that, and the second term looks like that, right? And then and the coefficients are given by these operators. So this can be viewed as the stationary point of the function, which is this one, dropping the coefficients. Okay. So we define what we call a reduced energy. That's now a function of all my free amplitudes. And this energy can just be read from here. Okay. So now remember, it's quadratic and cubic. And this is the energy now that we want to optimize. We want to find stationary points with respect to the case, and that will give me, well, that's a necessary condition for being able to draw a branch from this point. Okay, so we are sitting at a bifurcation point where we have multiple modes. We could try to construct different bifurcation branches by combining the modes differently. And that functional really tells me how it's possible to do. Okay. So all these coefficients are known. It's the known operators evaluated on these modes, which I know. So these are really coefficients I can calculate and have this cubic function to optimize. Okay. So that's how you would generalize the Lyapunov-Schmidt construction in the case of multiple modes. It's easy. It's just I mean, it's really the same equation as before, except that now we have many modes and these coefficients in between. Now, there's something very interesting that takes place with the relative instability, and that's deeply related to the underlying symmetries. That this looks like an ugly mess, right? There's a very strong and simple results that almost gives me the expression of all this without calculation, and I'm going to explain to you how this is possible. So the coefficients we need to evaluate, remember, so they are typically Q3 evaluated on some modes. Now, if you look at what needs to be calculated for that, so Q3 comes from the energy, so it's an integral over the volume of these things. So these things are complicated, but what we know is that these modes corresponds to wave vectors so it has some complex dependence, but there's something like that even in these terms, right? Just because these were derived by assuming a harmonic dependence on the coordinates, right? And the same with the third vector, for instance. Okay, and then this is multiplied by something here, which I don't know exactly, but has to be a function of z. And maybe lambda. But this part here doesn't depend on x and y, because all the dependence of x and y is on. Okay? So now, well, this is k1 dot x1, x2, x1 y, if you want. So that's the in-plane wave vector times the in-plane coordinate. And now we're doing the average of this thing over the entire slab, right? And in particular, if you think of a wide and a slab of large dimensions, you can think of this as an infinite volume. And you know that the exponentials are going to average out. So this will average to 0 unless the sum of the wave vectors is 0. Okay? It's called the resonance phenomenon. The reason again is that the factor here doesn't depend on x, y, and the only dependence on x and y that's introduced by these things comes from the harmonic dependence and okay, so it's easy to calculate the average. So we have what we call a resonance condition. And this is the lemma that I've written here. That says that any coupling coefficient is going to be 0 unless the corresponding eigenvectors with possible sign change sum up to 0. Okay, so now let's look back at the two things we have here. We have one coupling coefficient that involves two modes. Okay, so how can the sum of the two wave vectors be 0? Well, it has to be the same mode. Okay. So actually, you get a very simple expression. Well, okay, so Q, this thing has to be 0 if I and J essentially are different. And also because my system is invariant by symmetry, the results cannot depend on the orientation of the mode. So that's just the sum of the amplitude squared times the coefficient. Okay. And you can do the same argument for this other guy. So this other guy now has coupling with 3 waves. Remember that the wave vectors have a prescribed norm that is set by the linear stability analysis. So now for this term, if you want this to be non-zero, you need to find 3 wave vectors that have a given norm and that need to sum up to 0. The only possibility are the sides of an equilateral triangle. Okay. So the only thing that's happening here, the only coupling that are happening here are self-coupling and coupling between nodes that belong to the size of an equilateral triangle. So you can restrict to, I mean, you can restrict to just this situation, and that's n equals 3. And that's the only type of coupling that you get at this order. And if you do that, actually there's another trick, which is to use complex amplitude and not real amplitudes, because we have one cosine mode and one sine mode for every wave vector. So if you do this horrible mess that you've written here, just boils down to this. And the sign now are the complex amplitudes with which you combine all these modes. Okay, that's the quadratic term, which is just the sum of the moduli. And if you think a little bit, you can also show that the cubic term is just this, and it's the only way that you can be invariant with respect to change of orientation, translation, etc. And you can actually, you don't even need to assume that you can use your computer, calculate these things, so that would be the entries of a tensor, and you can recognize. So we started with a horrible mess, and we ended up with this. Okay, so now we have to find the 3 complex amplitudes, psi 1, psi 2, psi 3, that make this stationary, and that will give us the possibilities for the 3 modes to couple together. Okay, so it's a simple algebra exercise, and you find that, well, actually, I forgot to say that this gamma, there's this gamma coefficient here that still comes from the calculation of these explicit integrals, but there's only one coefficient at the end of the day that you need to calculate. And so this gamma can be related to the shear modulus of the initial modulus. So that's a nasty calculation, but it's the only calculation in the thing. So this gamma is a material parameter that captures essentially the moduli, the modulus of your slab. Okay, now you study the stationary points of this, and what you get is either, well, you can show that they are all equal, so there is no bifurcation by which, of course, the expression here is symmetric, and actually you find that the only solutions preserve the symmetry. And there are 2 possibilities. Either they are all equal to 0, which is obviously sufficient to make it stationary, and that's the unbuckled solution. Remember, we started from the bifurcated branch. 0 as a perturbation should always be a solution of the equilibrium. And another solution is very easy to derive. It's just this. And if you restore, so that's in rescaled variables. Remember, that's a complex amplitude. It has to be multiplied by eta, which we have used to renormalize the amplitude, and like we did before for the symmetric bifurcation. You can re-express this in terms of the original one. And so here is the bifurcation diagram that you get. So that would be the load. So that's the intensity of the weight, well, scaled by the stiffness of the material. And this is your bifurcation diagram. So you have the unbuckled branch, so that's the flat configuration. And you have this non-symmetric bifurcation, which is represented by this line here. And so that would be the amplitude of buckling. Okay, so you predict this. And along this line, it's just this equality here. Lambda 1 proportional to so lambda 1 is the load increment, it's proportional to the buckling amplitude. You can make the prediction because we can calculate this coefficient here, and we know it's sine gamma. With this theory, you can predict that for a typical constitutive load, if the load is less than the buckling load, you will have this type of pattern. So if you look from below, you'll see an array of dimples right? So at every center of the hexagon is going inward. And if you're on this side of the bifurcation point, you'll see an array of bumps, right? So the center of every hexagon is going downwards, so towards the observer. Okay, and I've forgotten to say the most important thing, that combining three waves with equal amplitudes when the wave numbers belong to the size of an equilateral triangle gives you the hexagon, which is the big thing we wanted to interpret from the experiment. Okay, and actually, I've hardly mentioned what system I was talking about. I've mostly used symmetry arguments here. Okay, to cast the general form into this particular one and simple one. So actually, this reasoning is applicable to any system that has the same type of symmetry. So I need a plane symmetry where all the directions of the plane are equivalent. So it's called transverse isotropy. And essentially, we've just shown that in transverse isotropy system, you naturally go to hexagons. So it's an argument that's been known for a long time in fluid mechanics, where there's a long history of pattern formation and so on. But essentially, that's the solid mechanics version of the argument, which is hardly known here. It's interesting. Okay, so then you can complement this analysis and look at what is the stability of the branches, and you find that all the branches here are unstable. The other one here is this one. You can do a fully nonlinear analysis, typically using a computer or doing some ansatz on the form of the solution, so approximate methods or computer, and you can do a complete bifurcation diagram, and you find indeed that your unbuckled solution stops here. It crosses this unstable, this folded thing here. It's the same as that. So you have one type of hexagon on one side, another type of hexagon on one side, but all are unstable here. But if you follow this branch, which is the array of dimples, this one, of course, it can go to very small loads, because for small loads, you only have one solution, which is the natural configuration. So it has to fold back here, and that's actually what's happening. We've checked that in numerical simulation. So it folds back, and as it folds, it becomes stable. So there's another branch of dimples that emanates from this bifurcation point, which you get here. So now what's happening in the experiments is quite clear. You get to this point where you have the linear bifurcation, and there's a finite amplitude jump to this branch. So that could be, that could seem like something which is hopeless to characterize analytically, but actually just the fact that this branch here is pointing in this direction and with this particular type of pattern really connects nicely with the patterns that we have here. So in other terms, using this quickly nonlinear bifurcation, you can predict that that there will be a jump, and you can also get a sense of what the patterns will be, and that's exactly what we check. Okay, and then that's what we see in the experiment, and that was the initial observation where the unbuckled branch, so that the unbuckled pattern is observed up to some critical load, which is significantly less than the load predicted by the easy linear stability analysis. So that was the finding before we started working on that. And then you find that there's a finite jump in the amplitude, so you get to hexagons of finite amplitudes from this point here. So that's really the same type of things that you get. So the load is it involves thickness, so it's rho J divided by mu h, I guess. I hope it makes sense from the dimensional point of view, because it's not that. Okay, so that's how heavy versus compliant or thick. I think it's maybe H. H is probably a both, right? It should be a both, I guess, because it's easier to buckle if it's thicker. Okay. So then I won't go much into this, but I just wanted to give an explanation of these nasty Q things which I've shown here, which I haven't justified. So where these formula come from, it's actually quite easy. but you don't really need that, just if you're curious. So remember, we wanted to expand the equilibrium with respect to lambda and some increment in perturbation. So it's just a Taylor expansion. You Taylor expand with respect to this parameter first, and you get these types of variations, and next you expand with respect to lambda, to this increment of lambda. And the point here is that what you get, so then if you do that, you have one derivative with respect to lambda and one derivative with respect to position, and this is exactly the Q operators that we've introduced before, right? So they are really sitting on the envelope punch. So these are the Q's, and if you do this expansion, you get many terms that have Q, some derivatives, and are evaluated here. So, and there's a third step, which is to insert the expression of x, of delta x and delta lambda, and you finally get the expression that are there. So it's not very nice, but it's just 3 lines of code with a symbolic calculation. And in any case, this is completely general, so you can just reuse the coefficients that are listed here in this expression will not change because all the cases are covered. Okay, so just a summary on what I was somehow hoping to cover last week, but I realized doing it was too much. So the linear bifurcation analysis is usually easy, at least for systems that are symmetric, invariant, or stuff like that, and it's quite common to do. It's a simple recipe that can be applied to any asteroid structure. You take the nonlinear equations of equilibrium, you linearize them near a particular configuration, and you find critical loads such that ghost modes or linear modes exist. Depending on the system you're considering, it can make predictions that are more or less useful. So for the relator instability, for instance, it will give you just an upper bound on the true load where you start to see the other patterns. And for some patterns, it can help predicting the wavelength, the wave numbers, or even the type of bucking patterns, symmetric versus non-symmetric, just by comparing the associated critical loads. And now we've seen this Coiter expansion, which is a nonlinear version of that, which is just a simple recipe that where we based on these operators. The explicit calculations, except for the elastica, can be quite tedious, but then it's really nice to use formal symbolic calculations, and it actually works very nice with symbolic calculations. You get the amplitudes of the branch, you get the oscillating parabola for symmetric bifurcations, or the tangent curve to the bifurcated branch. And you can learn about the nature of the bifurcation and also on the stability of the branches, except that was not covered in my presentation. And there's also this case where you have multiple modes, and you can decide, like we did for the elastica, for the relator instability, we can decide what's the best combination of modes that will actually lower the energy by essentially pushing the energy further. And another important aspect of this is that we can also account for imperfections, and that's going to be the topic of my following topic. Okay, so now, do you want to take a small pause before we continue, or do you feel like do you need a break, a small break? 5 minutes. Yeah, okay, let's take 5
minutes. There are some like a mixed mode between the strips and between the axes.
Sorry?
There's some mixed modes between the strips and between the axes.
Well, so the hexagon are really a mixing of the stripes. Never see the stripes by themselves.
You have some like this structure.
Oh.
I think something like that.
Well, right. Well, okay. So all what I've said here is for an infinite system. And now, as soon as you introduce boundaries and things, so what we're trying to calculate here is the minimum and now, if you can introduce defects and perturbation from a boundary, and then push the system.
So they used to have this one. So if you use the breakdown as a function,
it's equivalent to the particles on the surface of water. Because particles of the water you have
when they will organize. Yeah, there's some analogy. There's some analogy, but this is less geometric and yeah, you're right.
It's sufficient to solve the problem. So if that's not true, say you have a velocity dependence or like constraints, so like Thompson's you have to solve and their dimensionality problem. Well, minor generally lower, but minor generally lower. Yeah, this is supposed to be a conventional IPA calculation. But it's just I'm doing simple problems that usually solving you should be able to solve for it as a function. Like it's just a couple of equations. Yes. And I define the constraints for that. I can do work out of the fun. Well, it works. Well, yeah, I'm also yeah, so I have tried out a constraint on distribution of stress. Straight rate. Okay, so is it just like standard dissipation? Sure, it would be dissipation explicit to zero. Exactly. So, but it's linear. Yeah, it's a linear constraint. Yeah. So it is a velocity constraint. So you have to solve it explicitly. It's a rate dependent constraint. Yeah, it's rate dependent, but it's static problems. There's no mass. Okay. So, welcome to physical elasticity. But dynamic, except in terms of it's been a while since I've done it, so we're like, keep talking about rates, but mass never shows up.
Okay.
That's right.
So now I'm going to talk to two very tightly connected topics, which are imperfections and localization. So just in a few words, imperfection can really be important. We are talking about buckling, right? So we are talking about points where the structure has a soft mode, because by definition the bifurcation we've seen that the bifurcation takes place whenever the stiffness passes through zero in some direction associated with this mode. So imperfections or anything that we would typically not model in a simple tense like that, imperfections we tend to be enhanced by this zero stiffness. And I'll give you examples. Another feature is localization, where we all think of a nice sinusoidal mode, and I'm going to show you that it's under quite generic circumstances when you have an extended system with a size that's several times or many times the critical wavelength, then this situation is quite generic, and you see that a mode which is initially regular or spread over the entire structure tends to focus on one point, and that's the extreme case of focus. And again, that's very generic, and actually it analyze these two phenomena by this framework of Coiter's method. So I probably don't need to go through that again. And so I present these two models for the case of the strut on the foundation. So it's just an elastica that's sitting on some elastic medium, and a simple representation of the elastic medium would be nonlinear springs, which we take to be softening. I'll change to stiffening later. So meaning that the force, the restoring force, is below the one given by the initial tangent. So I'm showing you how the things work in this particular example. You could argue that we've dropped some geometrical nonlinearity here, so this term is linear here, and we've chosen to only retain the nonlinearity here. So arguably, many things can be improved here, but that's the simplest setting where I can make my points. Okay, so now if we take this beam equation with pre-stress here, I should say a word on this term. So that's the way we represent the imperfection here. So the idea is that we have some reference shape W0, and what we measure as W is the increment of displacement, and the curvature that enters into this balance of forces is actually the true curvature, so based on W plus W0. Again, there are different types of imperfections. So here, for instance, we don't use W plus W0 in the spring. So that's an assumption. It's saying that the springs are sitting on the ground, which has the same shape as the imperfection. Okay, we could do something else. We could assume that this is flat here, and then we would need to insert W in the middle. Okay, so different variants, many ways to introduce the imperfection. That's just one specific one. And by the way, here, because I don't have W0 in this term, that assumes that the imperfect shape is stress-free as far as moments are concerned, right? So any moment will arise from an additional displacement. So in rescaled form, epsilon would be the typical amplitude of the imperfection, and lambda would be the scaled load. And we've also rescaled the coordinate x, because you know that the system produces a given wavelength, and you essentially use this wavelength to rescale it. Okay, so let's start by looking at the perfect case. So we'll kill the imperfection, and it's the classical elastica. And let's start with the linear bifurcation analysis. So it's just looking at this thing. So it's the completely easy case, no imperfection, no nonlinearity. And then you have a linear equation with constant coefficients, so you can seek harmonic solutions. The wave number is going to satisfy this characteristic equation, which you can rewrite like that. And then you find that in the loading wave number plane, your critical condition is met on this parabola-like curve. And when you increase the load, the first point where you become critical is for lambda equals 1 in this specific set of units, and for a specific wave number, which again is 1 in this specific set of units. So that's the linear stability analysis, and you find that the associated mode is a cosine, which is not very surprising given the form of the equation. And just for later reference, I'll give a name to the operator, the linear operator that appears here when lambda is critical, and I call it LCL, like linear. Okay, remember this? So by construction, LC is 0 when applied to a cosine. And now, because it's a nice, well, actually, the reason is that this system has a conserved energy, so you can view LC as a self-adjoint operator, which is a complicated way of saying that if you calculate, so this bracket here is just the average of the product, and then you can show that because you only have even derivatives, if you calculate this times the v, you can move the LC on the v, and that's doing the integration by parts and transferring the derivatives or something like that. So the crucial thing here is that because you have this, you can view this as a quadratic form, and actually it's the form Q2 that we've been dealing with before. So all this is the same. There's an explicit form of Q2C, which is the one you would get if you would write the principle of virtual work. And so the load is here, but I've taken the critical value of the load, which is 1 in this set of units. Okay, so that's just algebra and writing. The only thing that actually will matter at the end is that if you, any results of this linear operator, if you combine it with cosine, which is our fundamental mode, then you get 0 on average. And the reason is that by this formula, you can transfer the primes on this thing, and then you find that it's LC applied to the cosine, and that's 0. Okay, so it's and so that's the property, that's a crucial property we use. And this is really the, so it's quite obvious for the system, which is simple, but in more complicated system, it's not so easy to identify unless you're using the virtual, the variational formulations and the principle of virtual. Okay, so let's add a single ingredient now, which is the non-linearity. And you restore this W cube term, but still in the perfect setting where you have no right-hand side W naught. So we can just apply the Coiter method and try to find the bifurcated branch for the system. So let's review this. And actually, I've written the energy here. So Q2 equals 0. That's what we've just solved in the previous slide. If you look at this expression, you only have even powers of W. So if you take the third variation and evaluate in the base state, which is 0, then you get 0, like for the elastic before. So this operator Q3 is equal to 0 to 0. And then we know that we are in the symmetric case, so we know that lambda 1 is equal to 0. And we can continue the solution procedure for the symmetric case. We need to solve for x2 with this right-hand side, but we are in a highly symmetric case where this is 0. So it's like before. X2 is actually 0, so there's almost nothing to calculate. And then we are left with the amplitude equation that's going to select lambda 2. This one is 0 because x2 is 0. So we just have to evaluate this and this, right? So we need to consider the force variations that come from this term. So that's essentially computing the average of cosine to the power 4 coming from this term, that's Q4. And we need Q2 prime. But then here, there's the only dependence on lambda is from this term. So Q2 prime is just going to be the average of the derivative of cosine squared. That's sine squared. Okay. So we just insert, remember the shape of the mode, and we have something which is very similar to the equation. Actually, it's the same equation I wrote on the board, but just with a different coefficient because the integrals evaluate to different numbers, and you get this amplitude equation whose solution is A1 equals 0, the fundamental branch, and this parabola here. And actually, it's even more clear if you multiply like I did before by eta cube, and then you have the real amplitude, because this one is the scaled one. This lambda 2 becomes the increment of load, and you have an implicit equation for these two sets of curve. And because the coefficient here is positive, you find that in that particular case, when we have a softening non-linearity, then the branch is curved to the left. So that's the case where you can expect unstable bifurcation. Okay, so it works really much the same. So now the question is, what is going to happen if we add some kind of imperfection in the system? And you know that typically you would break symmetry and you would transform this nice symmetric pitchfork bifurcation into these non-symmetric things, and that's actually what we will derive from the system. Okay, so now we remove. We don't want to tackle the two difficulties at once, so we remove the non-linearity, but we restore the imperfection. So this W naught is a given function. Okay, now it's a linear problem, and you can solve it by Fourier decomposition. And when you solve that in Fourier, this is just a multiplication by this thing, which is the Fourier representation of the operator acting on W. And so you find the actual W dividing the Fourier contents of this by this operator. Okay? And now, all the points of this is that this operator is the same equation as we solved for determining critical points. This denominator here is going to be 0 when we are sitting at a critical point. Okay, so that's the stiffness of the system, and you find that the displacement is the input divided by the stiffness, and that works everywhere except near points where the stiffness goes to 0. So that's typically the predictions that we can do when we vary the load for a given imperfection, that we'll have some kind of proportionality between the amplitude of, so A is a measure of the amplitude of W. It will be proportional to epsilon everywhere, but with a coefficient that will diverge. And actually, I dropped an epsilon here, which is the intensity below. And times the divergence, right? So that's typically the kind of curve that you have. And of course, the approximation of linearizing breaks down in the vicinity of lambda, because that's supposed to be small prediction, small correction is actually large. So based on this, we would like to start to understand better what's happening here, because it's not acceptable to stay with that divergence. And of course, we've dropped this nonlinear term, which can help fix things here. So I want to give you a heads up of what we're doing now. We can do two things. One thing is that we can focus on the harmonic perturbation. So we just assume that this W0 is a cosine. And that's what we will be doing first. And the reason is that what goes is the divergence here is the Fourier component associated with the critical mode. Okay, that's what makes it diverge. So it's interesting to focus on a specific type of imperfection. And then later on, I'll switch to a different type of imperfection. So this one is a little bit easier because it's a single frequency component. Okay, so let's recap what we have here. We have the perfect theory that predicts this parabola. And gives me, in order of magnitude, the bifurcated branch says that the square of the amplitude is the distance to the threshold. And we have this linear imperfect model that says that the amplitude of bifurcation is proportional to the imperfection epsilon. That's because I used the linear theory, but it diverges near the critical point. And I don't know if you remember back what we did in the first lecture. We are in a very similar situation where we have two types of approximation, one that ignores the nonlinearity, the other one that ignores the imperfection. And so they are mutually exclusive, if you want. And now we're interested in finding a theory that describes some kind of overlap. And that's what we will be doing next. So we will have to include both the nonlinearity and the imperfection. But the point is that if you know these two things, you can easily get a sense of what are the orders of magnitude of the various quantities in this region of overlap. So if you combine the scalings that you get here for one theory and here for the other theory, you find this just by eliminating A. Okay? So you find that the typical load range where the imperfection is going to induce nonlinear effects is given by that. Okay. Now remember that we are in a symmetric bifurcation, right? So on the bifurcated branch, we have this bifurcation parameter eta, and so we've expanded lambda as lambda c plus eta squared lambda 2, and that's the one we know. Okay, so it's a known coefficient. So the point is that eta is the square root of the distance to the threshold here. I want to connect with the other thing. So in terms of eta, that suggests that to get this improved theory, I should assume that the imperfection scales like eta cubed. Okay? If I don't do that, then I'll fall back to either one of these regimes. Okay, so let's do this and use this scaling we've just said. So let's assume that the intensity of the imperfection is eta cubed times epsilon bar. So this epsilon bar is now assumed to be of order 1. And we restore both the nonlinearity and the imperfection, and we try to solve this, right? So again, remember that I'm considering the case where the imperfection is harmonious. And so it's a nonlinear problem, and it looks very much like the one we've been solving in the perfect case by the nonlinear expansions, by the Coiter expansion. So what we've addressed before was the case where we had 0. Okay, and that's a term which is of order eta3. So actually, we can just try to reuse the Coiter expansion, plug in the same form of the same trial form of the displacement and load in terms of eta, and just redo everything. And because what we have here in the right-hand side is of order eta3, nothing changes for the first 2 orders. So you don't see the imperfection when you're starting this expansion. Are you okay with the big picture? No one is lost in the thing. So I'm studying a harmonic imperfection, trying to address both the nonlinearity and the imperfection, and for that I'm using a Coiter expansion. So nothing changed. So we get the same, we are building everything based on the same linear mode cosine here. At order 2, essentially we realize that there's nothing to do, and lambda 1 equals 0, and then we had this thing that we wanted to be 0, but now we have this extra term. Okay, and remember that right, this equation was in weak form, so we have to multiply by some W hat. Okay, so the last step was to replace W hat by the critical mode to get rid of terms here that we didn't want to calculate. And if you do that, we have the same amplitude equation as before, but now with this extra term that comes from the imperfection and times the coefficient. Okay. So we just change the bifurcation equation that we had before, and that gets a new term, which is just the imperfections. Now I'm switching back to the non-scaled version where I multiply again everything by eta cubed, and I make appear the non-scaled amplitude, the true load increment, and the true imperfection. Okay, so that's my equation. And you can use a numerical software to plot that. This is how it looks. And it's changed, again, the pitchfork bifurcation into one branch which no longer bifurcates, another one which has a 4 point. Well, actually, if you want to solve this equation, it makes sense to use scale variables so that epsilon is effectively equals to 1. So it's a simple algebra problem. And then it has this universal form, which really looks like this. Remember, you have this 1 over delta lambda, which is the prediction from the linear imperfect theory. You have this green branch, which is the parabola predicted by the perfect nonlinear theory. And then you have this extra curve here, which corresponds to the red curves, which by design matches nicely or tends nicely to the other asymptotes, right? So if you, for instance, the reason I'm connecting here is that in this equation, when I go to large A's, I can neglect this term and I'm back to the perfect theory, right? So by dropping one of the 3 terms here, you recover the predictions of the 2 previous theories, right? So it's really something that's more general and hardly more complicated. Okay, so then one thing that's of interest, for instance, is if I come from this almost unbuckled solution and now follow here, I'll get a bifurcation, a discontinuous bifurcation, and I jump to this branch. So that's going to happen near this point, which I call lambda f, that's the full point. And so lambda f is less than the threshold predicted in the perfect case. And you can now, using that, you can even predict where it is. And what you find is that there's a decrease in the buckling threshold, so the bifurcation is taking place earlier because the imperfection is helping the system bifurcate in some sense. And interesting thing is that it takes place with a non-integer, well, with it's not proportional to epsilon. It takes place with this fractional power. So it's inherently a nonlinear phenomenon. And you've seen that the linear theory was not actually able to predict anything sensible in this region. Okay, so that's really typical of imperfections. Well, the few things I'd like you to remember from that is that these imperfections fit naturally into the coiter expansion, and actually the coiter expansion were so popular because they were allowed to address the effect of imperfection, which are so important in some cases, like shell buckling. The effect of imperfection is intrinsically nonlinear. So typically, if you have a system which is perfect up to 1%, you can have a change in the buckling threshold, which is typically of the other 10%, because that's not very far from the square root. Okay, and that's exactly what people have in mind or what I had in mind when I was mentioning the importance of imperfection. Another thing is that, so here I've described the case of a symmetric bifurcation where the imperfect curve looks like that. But there's a case where, which I don't have time to cover, but just a drawing with surface. So if you have an imperfect bifurcation that has, particularly when it has a small scope, the imperfect curve would typically look like that. Well, it depends on the stability. Let's see. 7, 7. So this would be what I was calling 1 minus lambda f. And in the imperfect case, it has different scaling laws. It's not epsilon to the power 2/3. It's actually 1/3 if I remember correctly. So it's even worse. And that's exactly what's happening for shell buckling, that for a long time, for 30 years, and that's the work of Coiter, people have calculated the perfect bifurcation threshold for spherical shells, and they found a number that was twice as much as anything they could get in the most perfect set of experiments that they could realize. They had incredibly polished sphere with incredible tolerances, but there was still a 0.1% imperfection. And this 0.1% was entering into this term, rho to the power 1/3, and became a factor of 0.5. All right, so that's essentially what Coiter is very, very well known for. And again, I've shown you a case where it's not so critical that what you get by the perfect theory can be significantly different here, even though it looks like the imperfections are negligible. Okay. So now, right now we focus on a specific type of imperfection that was harmonic, and the reason was that this is the kind of things we can expect to resonate with the buckling mode of the structure. But now the question is, what happens if we introduce an imperfection that's a little bit more broadband, right? So let's not focus on the harmonic thing. So an easy way to do that is to consider, for instance, an imperfect configuration that has an infinitesimal kink, right? Small change of, it's been bent a little bit. So if you do the Fourier transform of that, you find that all the modes are present. And also it's nice because it complements the previous analysis, because that's really a localized imperfection, while the other one was periodic. So, and you see that there are interesting things that show that one have localized imperfection. Okay, so we studied that by focusing on 1/2. So we now be on the half domain. We introduce the imperfection by having this boundary condition that the initial slope is epsilon. It's a small number. And so that's where we introduce the imperfection now. We still have the non-linearity. And for the extra boundary condition, we use the natural boundary condition. So just the natural equilibrium. And again, we can start by, so we redo the same general scheme. We can start by dropping the nonlinear term and see what is the effect of the imperfection. So then it's a pretty easy problem, right? Because it's the solution is cosine, sines, and exponentials. It's a linear problem, so we can solve everything. So we can seek solutions in terms of decaying exponentials because we're not interested in things that blow up in this physical domain. So that's how we seek solutions. And then underlying this, there's a complex wave number that does A and B. And we can use the dispersion relation of this equation to set the wave number. So that gives me eventually A and B, which are the coefficients I need here. And you can connect A and B to this lambda, which is to this theta, which is itself related to group. So everything can be solved. And typically that's what you find. You find that you have the defect here. So that's W rescaled by the amplitude of the imperfection. You find that there's localized perturbation that decays off from where you want this. Now, what happens if you increase lambda and so that typically the solution I was showing would be this one, but now you can change lambda. And if you change lambda, and in particular if lambda comes close to 1, this theta is going to go to 0. And so B is going to go to 0 and A to 1. Okay? So in that solution, what happens is that this is less. Well, the decay length 1 over B of this thing is going to be larger and larger. And this is going to look like your critical mode, right? So this damped thing, which is the response to a localized perturbation, as you increase the load and come closer and closer to the bifurcation, is going to connect smoothly with the spontaneous buckling mode of the system, which makes sense, right? So the striking feature here is that there's a decay length here, which is this coefficient, and this one, so sorry, the inverse length goes to 0 near the buckling threshold. So when you take the limit of where you have an imperfection and an applied load, this linearity theory predicts that this is going to spread the entire thing, and eventually, actually, you can also see that it diverges in intensity. So we have the same type of breakdown of the linear theory because we are coming close to the bifurcation. It's a little bit more interesting than the pure Fourier mode because we have this extra wavelength or natural length that comes into play. Okay, and I think I'm going to stop here and we'll continue from here next time. So I want to stress, and maybe I give you an outline of what comes next, but no more. The result of this linear theory is that what you find close to the buckling threshold is something that's your critical mode, sines and cosines, times an amplitude here, which involves x, times a small quantity p. So that's a slow modulation. It's the modulation you see. Times coefficients here. Okay. And maybe that's reminiscent of the first picture I was showing of the floating elastica, remember? So it's not exactly in the same context, but when you have the floating sheet that's floating on water, it appeared to be almost regular, close to threshold, and more localized as you move away from threshold. And this is exactly the same phenomenon. Okay, so what I'm going to show you. Okay, so if we are now back to the imperfect strut, we have now a linear theory that works almost everywhere, except it diverges when lambda comes to 1. So in principle, we could do the same type of fixing that we did before, we could try to restore the nonlinearity and try to find a better theory that would handle, that would try to deal with this amplitude becoming finite now. So this is exactly what we are going to do, but we do in a slightly more general context. Essentially, we do it by temporarily ignoring or forgetting the imperfection. And so what we'll do is to, and this will be next time, we'll revisit the corridor expansion now, where the solution has some dependence on x, like before, typically the cosine, and some dependence on the slope variable, which would be the amplitude. Right, so the x is the slope amplitude. And what I'm going to show you is that you can redo exactly the corridor expansion, and there's only a tiny modification that comes in. And with this, we have yet another variant of the amplitude equation, where we have, like before, uniform buckling. But now we have an extra term that comes from the gradients of the envelope. Right, so this is a natural equation that will help us this type of modulation or localization phenomena. So by this equation, we can derive an equation for the envelope here and explain how much it localizes. And actually, there are different phenomena where this is useful, because that's completely, and that scheme of expansion is completely general. So again, it's going to be a variant of the corridor expansion we've been doing many times. But now, combining this, if you want, with this modulated form that we've guessed by analyzing the resulting imperfections. Okay? Well, see you next time then. That's it.
Thank you.
Tori, are you taking care of this, or somebody else taking care of it?
Right.
Wake up.
Okay. You're teaching here, right? Actually, raise the ball.
No, that's all right.